Welcome back for the second part of this afternoon school on Friday, October 2nd. The next lecture is about demystifying value categories in C++, which will be presented by Nils Meinert from the German Aerospace Center. Welcome, Nils.
Thanks. Can everyone hear me?
Yes. Very
okay,
clear.
Great, wonderful. Okay, so let me first post the link to the Indigo page where you can find the slides, because I've made some last-minute updates to the slides. These were really minor changes, but if you want to have the most up-to-date version, you can find them there. Okay, so this is the second part of my talk, and let me shortly recap what we've learned yesterday. So we learned that there are different value categories. There are L values and R values, which basically stands for left-handed and right-handed values. In older versions of C++, this was really meant as that L values can be on the left side of an equal operator and R values can only appear on the right side. Since C++11, things have become a little bit more complicated because we have introduced moved semantics, and this really opens the door to change the value categories, for example, by moving an L value and thus making it an X value. There was a question yesterday if there's a situation in real code where you where you actually using the two ref sign, and I struggled a bit with this question, but there's a very easy example whenever you do a move constructor overload. So if you do something like this in your code base, you say, I have a specialization for the case when the object should be constructed with an R value. And in this case, you definitely have to use the toRef symbol. Then I had one remark on this slide 31. Yeah, so I just wanted to mention that the value categories that we have are present in almost any programming languages which where you can reason about lifetime of objects. What is special about C++ is that from your code you can interact with this value category, and this is done exhaustively in the STL. So all standard library containers, let's say almost all of them, do this so that you can for example, move these objects, and there were clever people involved to actually do the heavy lifting of implementing what to do in these instances, and we will discuss some of this example later on in this talk. But in case you want to do this on your own, the first and easiest thing to do is, of course, to provide a proper move constructor, as we saw on the previous slides. But what you can also do is you can qualify your methods for being only called for L values or only called for R values. This is what we saw here, and this is really the point where you interact with the value category. So you can when this function is called, you know whether you are the object is just about to be destructed, or if this is just in the middle of some more complex logic. And the thing what we find was quite confusing is that R values can have a name, but whenever you use it by name, it becomes an L value, and this is what we saw here. But this is this is also the very nice thing about it, because you can be sure if this F is called, so where print B, then then the object is really an R value, and so it will during the next few cycles will go out of scope. Okay, so this was a short summary of what we did yesterday and a few remarks. And okay, so I ran very slow yesterday, so I will skip a few of the aspects today. So I will not give you in superficial introduction into a reading assembly. I'm sorry for this. But anyhow, I think I will be able to explain a few things to you, which might be interesting. So let's start our today's session here on slide 42. When taking integers as arguments, you typically use the normal copy by value semantics, but you could also do it by const reference. So, and the question is, if we have this really simple logic as shown here, is there any difference between both of them? Is there an approach which might be better to do? Because for more complex objects, we are very used to avoid any unnecessary copy. And so basically the way to go is always to take something by const reference. Let's look at this example. This is very easy. We take an x and we copy this to a. We call a side effect function and then return a minus x. And you can already see you might expect that the return value of this function is always 0, because basically what we are doing is we're calculating x minus x. So let's look into the assembly code, and I will just make this very superficial. So let's not look into the debug version, just directly jump to the optimized build 03. So you don't have to be able to understand everything what's going on here. The only thing that I want to show you is on the left we see the version where we take the argument by value, and on the right we see the version where we take it by const reference. And what you see is that the right version is much longer. And of course, this is just a very poor rule of thumb, but in general, you can think of more lines of assembly means slower execution, because the processor have to process more instructions. This is kind of surprising. And what we also see is that in the left case, so we take by value, the compiler already figured out the return value, and the return value in this case is always 0. The compiler is smart enough to see that it is more efficient to return EIX XOR with itself than returning 0. This is some kind of strange optimization, but this is basically the same as returning 0. So in this case, the compiler figured out what to do, whereas on the right side, the compiler wasn't able to do this. Where what he has to do here is he really has to store the value of x, so the argument that is passed, then calls the side effect function, and then later on reload everything. So he's not. I mean, obviously these are not very few. These are not very much instructions, but there's more work to do. And why is this? So let me go back to the source. So what you see here is that the compiler directly can optimize this to 0, because nothing can happen to the value of x. Whereas on the right side, in theory, I mean, we don't know what side effect does, and the compiler does not as well. And since we don't give this the implementation here, this, for example, this could be in some other file when we don't have enabled some kind of link time optimization. This is really the best the compiler can do. He has to assume that this x is changed by calling the side effect function, even though the argument is marked const here. But this const also, of course, only holds for the context of this function. Outside of this function, since this is a reference, it can change. And the function side effect could potentially change it. So the compiler will not optimize this. So what we see here is that it's actually more more expensive to pass something by reference in this very simple case. And this is exactly the message that I want to convey here. You should see is that when you have primitive types like ints or so on, they're extremely cheap to copy, because they in principle just go by registers, and this is the fastest you can do. And then you're given the compiler a very hard time if you do some level of indirections here, and you will pay a performance penalty in this case. And there are some questions going on. Let me just read those. So the question is, are this example with no optimization? No, these run with O3. And you can even do some more optimizations, but the problem is that you don't know what side effect does, and potentially it could change X. So no optimization will help you here, besides link time optimization, of course. Yeah, I think they're optimized. Yes, O3 as a flag. Yes. How side effect can access X? Well, in any case. So so the question is, why could side effect change X? Well, X was passed to F, and we don't know where who else is referring to X, and side effect could do this by having a side effect. That was the idea behind the name. Okay, I don't see any further questions. So let me continue. So we already have this. So there are also other cases where references are not not the best you could do. So let's let's consider the example with strings. So string is not a simple type; it's a complex type, and in fact, there's a lot of going on here. And let's say we have a function getSize which returns the size of the string. And of course, since we don't want to change anything, and we don't want to copy a string, which could be very expensive if the string is not optimized with short string optimization. So we're taking this, of course, by const_ref, and then return the size. Since C++ 17 or 20. I'm not sure about it right now, but you can click on it. I think string view is the 20 feature. You could also use string view, which is exactly what the name suggests. It is a view into a string, and as a rule of thumb, you could say that whenever you take something by const_ref, whenever you take a string by const_ref, you should consider it maybe replacing it with a string view. And one reason for this you can see here. If we call the exact same operation on it, so returning the size of it, then the assembly on the right is much shorter. So this is again optimized with O3, and so the mapping between the lines becomes very strange because there's no real mapping here from the code. But what you can see here, this is the first implementation, and there's some jumping going on. And whereas in the second case where we have a string view, this is basically the fastest that we can get, just directly return the size of the object that was passed to it. And the size in the string view is passed in the RC register. So why is this? Well, string can be short string optimized or not. So this is something we have to check first, because the semantic meaning of our bytes is different in this case. So we have to check first how to decode the bytes on the registers that are passed in order to know which of those indicate the size. And there's nothing we can do to avoid this, more or less. To confess, when you're going to Lipstadt C++, these guys made a cleverer implementation, and there you can get rid of it. But what I want to say is that this is a very good example where using a view instead of a const_ref can be more performant. So this is the case for string view. But also for span, for example, this is definitely a 20 C++ 20 feature. So so what holds for string also holds, for example, for vectors, where you should use span if you really only use a view into the data. Okay, so any questions so far? This seems not to be the case. Let's make a short quiz, but I don't have a create a poll for this, but I will give a short time to guess. So what do you think? Does this program compile? I give you a few seconds to think about it, and of course you can use this time to ask questions. So, well, will it compile? Well, it looks fine, right? We have a span, and then we pass something to it, and I've copied the header of span down here. Well, it takes an array by const ref. So does it compile? No, it does not. Why? Well, because references, and we're taking reference here to automatic storage objects, are not constant expressions, and this is exactly what a constant expression of a std array is. So by having this very general this idea, by just taking something by const ref, could stop some very easy snippets of working as well. Of course, the solution here is to make the array static, and this is something you should anyhow always consider. If you have some const expr object laying around, you might want to do this static anyway. So when you do the static, then it's not an automatic storage object anymore, and this this will work. And of course, the same also holds in the case when the scope is very clear set, and this should already work with C. Oh no, we're using span, so this is C++20 code. But without the span, this should also work in 17. So when the const expr is moved to the entire function, then this again works. But this was just a small example where you can see that even code can stop working if you're using const references. Okay, so this is the point where I wanted to stop yesterday. I had this short quiz. I will also skip it, but maybe you can think about it at home. So the question is, I have this function fx in Python, and you should find all x where this returns true. But the snippet is in the slide, so you can think about it. So let's talk about dangling references. Oh, I see there was a question. No template instantiation of the array X. You mean that there's nothing going on with this angle brackets here. So this is because compilers are not smart enough to figure this out. Not in all cases, but here it is enough, because you're passing X, and first in this place, the compiler can count the number of elements. It's an array, so you have to pass them at compile time anyhow, and it also infers the type, since everything basically the compiler does a comment type here, so comment type t, and of the comment type t of these things is an integer, so it figures out the type of the array, and then the same for span. Okay, so let us talk about dangling references. No, this is not a question, but the next will be let us have a look at this example. The question is very simple. I don't even ask for the output. The question is simply, will this compile? What we have a very simple struct s, which stores an integer x, and we have a function f, which generates such an object s and then returns it. Okay, so this is very simple code. And in the main function now, we call f and store this in a reference. And so this could be tricky. And in fact, if we try to compile this, we get a compilation error, which says that it is not that we are not allowed to bind a non-const lvalue reference of type as ref in this case to an rvalue. So so the problem is that the thing that gets returned from this f has no name, so it's an rvalue, and we try to bind this to an lvalue ref, and this really doesn't make sense, because this would indicate that someone else already has control over it, and we want to be we want to be able to see all these changes. This goes through f, but this is really not sensible for an temporary. So it's an rvalue in this case. So this is easy to fix. We can put a const in front of it, and then everything compiles. But even though this compiles, this looks kind of strange if you think about it, because we are taking a reference, and in this case const reference, to a temporary. So at the end, so at this semicolon, the temporary goes out of scope in theory, and then we are then we have a reference to something that already went out of scope. So even though this does compiles, are we invoking undefined behavior here? And this is now a poll question for you. So let me start it. And again, this is a very good time to ask questions if you have one. So you're actively voting. This is very nice to see. I'll give you a few more seconds. Okay, so let me end this here and share the results. You now should be able to see the results. So most of you think that this is indeed undefined behavior, and it is not. Why? Because there's something like the lifetime extension, and this is something you could consider this a corner case in the C++ standard, but it's really an important one because this is before thinking about it, everyone might expect this to work, and this is indeed what the standard says. The lifetime of such an object is extended if you are referring to it by const ref. And the const here is very important because otherwise you could change the temporary, which is really strange to think about it. And this is why we get the compile time error in the first place. And so whenever you're referring to a temporary by a const lvalue reference, then this is fine, and the lifetime is guaranteed to be extended to the lifetime of the reference. Okay. So maybe this is good to know. Let's think. Let's have a look at a more involved example, and I will give you time to read through it. But let me give you a very short explanation of what is going on here. So let's start with the main function. In main, we create an object of type B, and in order to create an object of type B, we have to pass it an object of type A. And then we do some printing and evaluate some values. So now I have a look at the details of A and B. So A just holds an integer, that's very easy, and B holds a reference to A, a const reference. And in order to see what is going on, I have I've implemented this log function, which just prints out on construction and on destruction. And we pass it an ID, so we see that we see the object that invoked this behavior. So and this is now a question again for you. So what is the output of this program? Let me start the vote. So it's interesting to see the number of people who vote I hate C++ is still growing. So this is a complex example, I agree, so I will give you a bit more time. Okay, so let me end this here and share the results. So it's interesting to see that most of you agree that you hate C++. So let me stop it here. And then let's dive into it. So the result is this one. And this is really dangerous because this means that we have dangling references. So the A1, B1 shouldn't be a surprise. This is just the creation. We start by creation an object A, and then we create B. So this is obvious. But then, and this is now the problem, directly after we created B1, and this is before X is called, the destructor of A is invoked. And since we only created one instance of A, this we can be sure about this because we only see A1 once. So this object is directly destructed after B1, the creation of B1 has finished. Then we append our X, and then finally at the end, B goes out of scope and the destructor is called. So this is exactly what we could have expected in the previous example, because we are holding a reference to a temporary. A is a temporary here. It's an R value, and we take it by const ref. And as soon as the constructor here goes out of scope, so basically by this curly braces, the destructor is invoked. And this is most likely definitely not what we intended. And the problem here is that this lifetime extension, which saved us in the previous example, does not hold if anything is more complex than the example on the previous slide. So in this case, it does not hold for any sub-expressions. The good news is that you can catch those things with address sanitizers, and I encourage you in any case to use as much sanitizers as possible, and especially use address sanitizers. So if you use those, they will in almost any circumstances will find such bugs. So this is really to encourage you to use address sanitizers in your code. Okay, okay, this was somehow an involved example, and you could see, you could think, okay, why should I ever implement something like this? So, well, let's have a look at this example, and this is something I stole from the Great F-Style blog. So think about a for each loop, where we create some kind of string. So we do some string concatenation. And then pass this to a function that is interestingly called already explode, and which takes the string by const ref. This is exactly what we've seen before. And at the moment where the constructor is done, this string will go out of scope, and we will have a dangling reference to with our for loop. So, and this is, I think, something which is very easy to write. Okay, so there's a question in the chat. Can you repeat why B2? So I guess that refers to this example. So this B2, well, this is the destructor of B. And when B goes out of scope, this is basically here, or a bit more precise, this is the case when we hit the closing curly brace here, then B goes out of scope and the destructor is called. This is why we see B2. Okay. By the way, I did a very poor job in indicating what where links are. But for example, you can click on address sanitizers when you have the slide sets available, which will bring the Klang sanitizer address sanitizer. So we have this. So what about this program? When you see this, doesn't this look like valid C++ to you? And this is not a poll question, but I give you a few seconds to think about it anyway. And of course, the answer is no. Again, dangling references. Where? Well, the index operator returns a reference, and we take this reference. So this is not a universal reference, which would also work and has the same issue, but we're just taking the reference. And so up to this point, everything is fine. But this is already a code smell. Why? Because when we change the vector, and we do so by doing a pushback, then we risk that the memory layout will change. And this is exactly what is happening here. A vector typically, well, this is, I'm not sure whether this is really stated in the standard, but the STL implementation of vector starts with a size of 0, then goes to 1, then to 2, to 4, and to 8. So it grows by powers of 2. So by at this point, it has a size of 1. Then we push another element, and then it has to reallocate, and now reallocates for a vector with 2 elements, and then move or copy, do mem copy of its value to the new storage location. But this reference will point to the old one. And so we were pointing to some dead memory. Well, so never do stuff like this. And again, use address sanitizers. They will warn you about this. So the question is, but it could work if there's enough space at the original location. Well, it's not about the amount of space that is, yeah, okay. So you mean this really is only the case in this circumstances where we have, where the capacity equals size of vector, and then we have to reallocate. If we take the reference now, everything should work unless we have less than 4 elements. Again, when we hit the boundary of 4 elements, then again we have the same problem. Okay, yeah. So there's the comment unbelievable but understandable. Yeah, that's what I thought when I first found out about this. But again, use address sanitizers that will warn you about this. So let us talk about std move in the wild. Let's do a very quick bench test with micro benchmarks. Let's think about a very small string with a value small attached to it, and then we copy this small string, and then we do the same with std move. So this is our first benchmark where we have our benchmark is called copy small string and move small string, and then we do the same for longer strings. So this is definitely too long for short string optimization. So we copy the string and then we move the string, and then we look at the benchmark, and this is the result. So no surprise here that the copy of the long string takes more time than moving the long string. And of course, these operations are much slower than those with the small string. But what we see that for the small strings, the move is actually slower by 20% as the copy. And this is interesting because if this should be the bottleneck on your program, moving just gives you a 20% performance penalty. Maybe quite interesting to see. So why is this the case? Well, for copying a small string, you just copy the allocated data, and this is for small strings. This is incredibly cheap because small string optimization means that you basically sit in your registers. Whereas when you move the small string, you not just have to copy the allocated data, which we already had to do in the first place, because we just have registers. There's nothing more efficient than we can do to just copy the registers. But we also have the string. We also have to set the string length of the move string to 0 to be in kind of a valid state after moving. And since the first operation is already quite cheap, this can give us, so just setting one variable to 0 can already give us a 20% performance penalty. And of course, I have to say these are micro benchmarks, and that these are not at all representable for your code base, presumably. But it's maybe good to know that moving is not necessarily always better than doing a copy. One other thing, let's talk about std map. Since C++11, the constructor of std map looks, the move constructor looks like this. And std map also has an assignment operator, which takes an rvalue. And so this was the case until C++17. And since C++17, this one was changed to be no except. And the question is, okay, in C++17, they changed a lot of things to C++20 and even more in C++20. Did they just forget about the constructor? And the answer is no, they did not. It's just not, they cannot just mark it no except. Why is this the case? Because the move constructor needs to allocate memory for its handle and nodes, because you are just creating an object, and so you have to allocate memory, and allocating memory can potentially throw exceptions, even though throwing exceptions when you're running out of memory is a very strange concept, because if you're running out of memory, allocating memory for the exception you want to throw is also will throw an exception. So throwing an exception will most probably in this case also throw an exception, but this is another thing to talk about. But this is the reason why the move constructor is not marked no except. Whereas the move, the assignment operator can be safely marked no except, because here at this point you already have two instances and at hand, and you can just cheat by swapping the pointers to it. And this is the reason why the move is so cheap compared to the copy, because in the copy you of course have to copy everything, and here it's just enough to swap out two pointers. But the thing that I wanted to mention here is that a move constructor can allocate heap space, which is nothing what I found out, but Ben O'Neill, for example, in this Twitter, this tweet. Okay, so any questions up to this point? Okay, so let's look at this benchmark now. Well, there's some weird stuff going on with lambdas, but what is happening here is we create a map where we store some elements in it, and then we return it. And the lambda thing is just to have really shorthand notation to mimic what happens on a return of a function. In this case, the function is a lambda expression. And so what we're benchmarking here is how expensive is it to create something in a function and then return it, just plain old return, and compare this to the case where we try to be clever and think, okay, so we created such an object that map in this function here, and now we don't need this anymore. So why should we return it and risk the copy, then invocation of a copy? We don't need this m anymore, so we can just move it out. So this should be more. This should be cheaper to do, right? And then to have some baseline, we consider the case where we really copy in map. So we have a map here and a map 2 here, and we just copy both of them. And this is just to have to baseline. So the baseline is on the right. So this is the copy, and of course this is more expensive than doing anything else. But we see that to do it by plain old return, this is faster, 10% faster than to enforcing the move. So this was the case where we returned the move of the map. Okay, so again, very interesting to see. Okay, so there's a question, but isn't the map M destroyed after going out of scope anyways? Why move? Yeah, so this was the idea behind this. The idea behind this possible and this potential improvement. We say we don't need M anymore, so why destroy it and copy it to some other object? So let's move it out. And we already see that this was not very smart to do. And let's think about why. So before answering this, let's look at this problem first, and we will come back to this. Think about a very simple struct, which just holds a pointer, and then if invoked with a certain size, it allocates memory, and on destruction deletes it. So typical AI container. Then we have an init function where we create such an object and allocate space for 3 elements, and then we assign values to those, and then we return this object that we just have created, and then we call this function init because this basically initialize our object, and then we can work with this. For example, in the main we call init and then access the 3rd element. So does this code bother anyone? Well, it is kind of strange because when we hit this curly brace, D should go out of scope, and when D goes out of scope, then the destructor should be invoked. And so if this is invoked, the array is cleaned, and we don't have any copy things going on. So this should allocate should access the allocated memory. So does this work? And I'm running quite late in time, so but you can convince yourself by the Scottbolt link here that this actually does work. So we should definitely talk about what happens on return. There are two parts of this answer. The first thing is this one, and this is again a question for you. Do you think that this program does compile? So we have 2 structs here, A and B, and 2 constructors. One is marked explicit, the other is, well, it's implicit. Well, then we call it here. So the question for you is, does this program compile? Let me start. So we now should see the vote. So even though this is arguably a very dry topic, you're very active. That's really nice for me to see. Okay, so let me end this here. Share the results. So I now should be able to see the results. And so most of you think that this program will not compile, but still almost 40% is sure that it will compile. So let me stop the sharing here. And in fact, it does not compile because of the second line here, on line 16, because it does not know how to convert a 42 into an object of type B, and this comes down to our usage of explicit. So just to remind you, what does explicit mean? When we don't state there's some, when we don't use explicit, everything is implicit, and we have an implicit conversion is going on. This is this is kind of interesting to see and dangerous because objects can implicitly call constructors that you might have not intended for usage here. So, but sometimes it's just helpful to have something like this. For example, the stood optional constructor is not marked explicit. So whenever you have an integer, but you need an optional, there's an implicit conversion going on, and the optional constructor is called. This is why you can have something that looks easy like this. You return 42 from your function, and but it will convert it to an optional. And that's also the reason why this works, because this is not a string. This is just a const char ref or const char pointer. And but what you need is a string. So there's a conversion going on from a const char start to a string. Okay, this was just to remind you. So this was the first point. On return, there's typically always going on a conversion, either explicit or implicit. Then there's another thing. Let's really disable all cool features in the compiler and forbid the compiler to do any elision of constructors. And so then we have a function, a struct, which logs everything that is happening. And then we have this function f, which returns s. That's all. And then let us see what's going on here in main. We create such an object, and then we call f in two ways. Once with an assignment, and the second time we directly construct an object s, which we name s2, by the result of this function. So the question for you is, if we run this program and have compiled it for C++14 and with no elided constructors enabled, what is the result? Let me start the poll. So it's okay. I'll give you a few more seconds. Okay, and stop it. So I now should be able to see the results. So most of you think it's AC, ACC, ACC. And this is not very nice for me to see, because this is actually the right answer. Let me stop. So if we really tell the compiler to do not elide any constructor, and interestingly, this is only possible until C++14, because the elision is guaranteed since C++17. That's why I really had to add the switch for 14 here. So, but you see what could potentially going on here. So a lot of calls to the move constructor. In some sense seems to be unnecessary, because in principle we only need this once. So for each call, of course, but we only need this once. We construct it, and then we basically just pass it through our layers. So this is somehow unnecessary, and this is also what C++ thinks about it. And when you run the very same program which just was in C++17 mode, then the result is just AAA. And this is why I made the question before, the poll before, that you can now really appreciate what the compiler is actually doing, because there are lots of things going on return. We first have, of course, this conversion, but also a lot of copies are elided for us. So why is this the case? Well, this is RVO, return value optimization, and already saw this the answer in the chat. And there are some people, for example, Ben Dean, consider RVO to be the most important optimization compilers actually do for us. And so let's for the rest of this talk, let's talk about RVO. So RVO or copy elision is the mandatory elision of copy and move operations in C++17. Whenever you have an PR value in the return statement, the construction, or to be more precise, the destruction will be skipped by the elision of unnecessary copy steps. So and this is very interesting to see that the standard committee was willing to add this to the standard, because it is possible to have code bases which in some sense rely on side effects of copy constructors. So now you cannot, so with this copy elision, suddenly code that where you expected to have these, for example, in the previous case where we had this ACC going on, when you really rely on the invocation of these copy constructors, you will now, the behavior of your program will now change. But the reason why they did it was presumably that they said whenever you, when you rely on side effects of your copy constructor, your code might be broken anyway. So the most drastic side effect that we can do to an copy constructor or assignment operator is to delete it. So if we have something like this, every copy should be permitted, and we should get should not be allowed, and we should get a compile time error. And code like this shouldn't work. But this is exactly the magic of copy elision, that it is allowed to skip any copy and move instructions, even though they have side effects, and this already includes if they are deleted. So this is proper C++ code, and this will compile due to the copy elision. Because the thing we return here is in PR value. It doesn't have a name, and so the copy is elided. As soon as we get it a name, this will stop working. Okay, so well, this was the reason why I wanted to introduce you to some assembly code, but since we are very late in time, we also just skip it, and I will try to give you the gist of it, so we don't have to understand really what's going on here. Because compilers generate different code if if constructors and assignment operators and so on do have side effects, and all this logging that we were using before are side effects. So it does not really help to do the logging if we want to investigate how programs will behave when there are no side effects going on. So the best thing to understand RVO is to have things with no side effects, and then look into the to the assembly code. And so what we're doing here is we have a function f and a function g, and in g we call f. And on the right we see the assembly code, and the only thing that is really necessary for us now is that we have a look at these call things here. So here, so we are looking at the assembly of g, the function g, where we call f here. And we can then just see the calls to the constructor. So there's a call to the move constructor here going on in G. Then there's a destruction going on, and another destruction. And this is with no elide constructors enabled. So we are so just in G we destruct S 2 times. So this is the benefit. Sorry, so in F, we generate, we have 2 calls to constructor. So this is the constructor where we created. Then we have a move constructor called, and then just 1 destructor. So in the end, everything lines up because this is 1 less destructor than we need. And this second destructor is called then in G. When we now turn when we now go to a return value optimization, all these things are elided. So when again we look at F, where we had these 2 calls to we have this 2 constructions going on and 1 destruction. With RVO we just create one S and no destruction, and the same for G. In G, before we had 1 construction, 2 destructions, and here we now have just 1 destruction. Okay, and this RDE, these are basically the this pointers, and I would have explained to you if we had gone to the more detail into the assembly code. But the slides are online; you can have a look at them. So let's have a look at this example. Will we have RVO or not? And in fact, in most of these cases now, it is technically NRVO, so named return value optimization, because pure RVO, so what RVO stands for is return value optimization, only holds for pure R values, and pure R values don't have a name. And in these instances, we always use now names to them. So there's extension to RVO and RVO, and there are no strict rules like for RVO. But in some cases, we will have the same benefits. But this is where things now becomes really interesting, because pure RVO is very easy to figure out, because whenever you turn a PR value, you will have RVO. But the rules for NRVO are more complicated, and well, they're not really stated, and it's up to the compiler how to optimize your code. But let's have a look at it. So technically, we are talking here about NRVO. So we have 4 functions: F1, F2, F3, F4, and we create objects here and then return them, or return them by move. And so what do you guess? What is RVO going on here or not? Since we're running late in time, I will just directly give you the answer. So in the first case, we will have RVO. You can think about it. Well, it's not pure RVO because we have a name here, but the code would be the very same if we would just return S and then curly braces. So this is absolutely the same, and this is why we would see this is the very same as we saw previously. And if you don't believe me, we can always go to the links and then do the same the same call counting we did previously. But again, since we're running quite late in time, this is maybe something you would want to do at home, or just believe me. So here, this is RVO. This is when we look at this, we will see an additional call to the move operator. So no RVO. Then F3 again is RVO, and F4 is again we will see a call to this copy constructor. So for the lvalue ref constructor, which is, well, kind of interesting to see, because maybe the intention doing this was to have to elide some destruction and do some performance improvement, but instead this silently reverts to a copy. This is the opposite going on here. So this is interesting. So there's a comment: I didn't expect RVO in F3 because of const qualifier. So let's have a look at it. Maybe I'm mistaken. So we have F3. And yeah, but F3 is RVO. So you see just one call to the constructor. And I think the reason for this is that the fact that this object is const only applies to the context of this function. After you turn it, the const qualification is gone anyhow. So this is clearly an optimization of the compiler. And if you would go to O0, for example, you will not see RVO here, but this is an optimization the compiler can do, because this will not change your program in any way, because, as I said, the const is only applies only to the context of this function. So I think this is again something I will answer for you. What about this? So we now have our function where we disabled anything that go wrong. This is a final class, and everything is no except. And then we have a function f, where we know we would see return value optimization if we would return s, but now we take a reference to s and then return t. So what do we think? Is this NRVO or not? And no, it's not. Here we again have to pay the construction of an object, where I don't really understand the reason, but again, NRVO is not guaranteed at all. This is up to compilers to optimize around it, and it is really nice to see that compilers are clever enough to do NRVO anyhow. So, well, it's maybe not so. We shouldn't be surprised if we don't see NRVO somewhere, because this is already a quite important feature, which is more like a gift. So, but in this case, no RVO going on, but I don't know why. And this, of course, could change in future versions of compilers. So maybe check it again 1 year later, and maybe then compiler will make this an RVO. So, and this is again a question for you. So what do we think, an RVO or not? Let me start the poll. Okay, let me stop this here. So, and most of you think that we will have an RVO. And it's of course quite unfair to do. Let's stop the sharing here. Because in the first case, we will have RVO. Why? Because the reduced type of the ternary operator here is very easy because it's in PR value. That's the reason why we see RVO. But in this case, it will not, because this is an R value, this is an L value, and the deduced common type will be an L value reference, and therefore we won't see an RVO here. So now I'm already out of time. So let me just close with the words that things can be even more complicated, like in this case, where lots of copying is going on, and doing std move in these cases are actually better than relying on RVO. So there is absolutely no golden rule. Return std move is not always necessarily code smell, at least not yet. You should use pessimizer move for GCC and Clang, I guess. At least for Clang, this should work. Which will warn you if you're pessimizing the RVO by using std move. And this is something that's is already changing. So in C++ 11, only pure PR values were affected by RVO. Since C++ 20, also rvalue references will work. But at the time where I prepared this talk, this was not yet implemented, but this is already half a year ago, I guess. So maybe this is already implemented. Yeah, but what I wanted to say here, it is complicated, and I have a lot more, and I have to skip the entire topic of perfect backwarding. Sorry for being so slow in this, but yeah, I think we don't even have time for questions. But any time that is given, I will take to answer questions if you have one. So thank you very much for your attention. Okay, then let me say that you can always ask questions also in the MetaMost channel, and I will try to answer them during the next days or so. So whenever you have questions, just reach out to me. Thanks.
Elma, I think you're muted.
Oh, I'm sorry, really. I wasn't muted, I forgot to mute myself. I was saying that it's a pity that time is passed so quick, because you have a lot of interesting things to tell, and yeah, now we have to stop here. Thank you very much.
Yeah, but it's my fault. Thanks a lot.
Yeah, thank you very much, Nils, for your great contribution with your 4 lectures on modern C++ in different themes, and for your demo section on Lambidas. So it was a big pleasure to collaborate with you for this school. Thank you again. And yeah, let's now have a quick break, and we'll be back at 4:20 for the demo session. See you in a few minutes.